Hi, good afternoon, and welcome to the IGLUNA First Space Expert Talk. Today, we're excited to have Philippe Ludivig joining us. He's working as a Rover Navigation Engineer at ispace. And ispace is a Japanese company which has offices in Luxembourg. They develop landers and rovers to use the natural lunar resources for moon based infrastructure in the future. Philip will talk about his experience about iSpace and compare rovers made for Earth applications to those that are made to go to the moon. And this will last for the next half an hour approximately. So please submit your questions in the YouTube chat, and after his presentation, Philip will answer them. Thank you very much. Welcome, Philip, and thank you for joining us. We look forward to your talk.
Hello, everyone. I'll give my presentation here. I'm, as mentioned, working for iSpace, and I specialize in R&D on rover navigation. So my presentation, I will talk a bit about my background, how I got to work at what I do now. I'll talk about iSpace, then I'll talk about the surface robots on the moon, and then we'll have questions. So my background. I have a bit of a weird background getting into the space industry because initially I actually studied computer animation and visualization. So I worked as a visual effects artist, doing image processing, but very manually. And then I decided to do a degree in computer sciences, even though previously I'd done already programming. So for my visual effects work, it was a very technical degree, and that's how I learned to actually do programming and dealing with computers. And then I decided I wanted to do more automated image processing, and the space industry seemed really interesting for that. So while I worked for a while at the university, I was at the University of Luxembourg on drones and UAVs, doing image processing for those. I eventually got the chance to become a trainee with the European Space Agency, and that's how I really got into the space sector. And in the meantime, I've also got the chance to work in the US briefly as a researcher, also with regards to space robotics. And now I'm a researcher at iSpace working on rover autonomy, essentially. But enough about me. So I'll talk more about iSpace in general now. So the goal of iSpace is to expand the human presence beyond Earth, and specifically to go to the moon. And on one hand, to deal with the transportation to get to the moon, but on the other hand, also to provide infrastructure on how to survive on the moon, how to keep systems running on the moon. So as mentioned, iSpace is a Japanese company. Our headquarters are actually in Tokyo, but we also have offices in the US and in Europe. And while the main work on the lander development is done in Japan, in Europe, we focus more on the rover systems and the rover autonomy. And we also deal with mission planning and processing of orbital imagery from the moon to enable mission planning. And today we have over 100 employees working for us worldwide. So we initially got funded through the Google Lunar X Prize back in 2007. So the X Prize was a $10 million prize to see who could get to the moon first and drive 500 meters. We were out of the 34 teams. We were one of the 5 teams that were selected as finalists. And we also won the mobility prize for the rover we developed for this mission. So here you can see our fully flight qualified rover that only weighed 4 kilos with everything included. And this is what we developed for the Google Lunar X Prize. The one thing we didn't do at the time was build our own spacecraft, because we quickly realized that the cost of doing this is very, very expensive. And so we decided to team up with other teams to get to the moon. But as you all know, the Google Lunar X Prize came to an end without anyone managing to do this. And essentially, we realized that if we wanted to go to the moon, at least today, we need to build our own spacecraft. And that's what we set out to do at the end of the X Prize. So back in 2017, we raised about $95 million US to build our own lander. And with this lander, we then want to go to the moon and take our robotic systems. So just as a little teaser here, this is the actual spacecraft that we're currently working on to send the rovers to the moon. And so the first mission we have planned currently is slated for 2021, where we land on the lunar surface. And to get into space, we work together with SpaceX, who will get us to a geostationary transfer orbit. And from there, we'll use our own propulsion to go towards the moon, to do an orbit insertion, and then to land on the surface. And already for 2023, we have another mission planned where, again, we will land on the surface, and this time we'll also bring our own rovers and we'll do more exploration of the environment around the landing sites. So this is where there will be a little video on explaining how the mission looks in the end. Okay, so this should have given you a good idea of what our first mission will look like. But the first landing isn't our own goal. We have a bigger roadmap than this. So just to emphasize on this, here you can see how we're planning on achieving a sustainable economy on the lunar surface. So we started with the Google Lunar X Prize and building our first flight hardware. And currently, with the funding we've raised, we're planning to achieve those 2 missions that I've mentioned. But further than that, we really want to achieve regular transportation to the lunar surface, because to build any sustainable development on the lunar surface, you need to have the transportation problem solved, and especially at a reasonable cost. Currently, it's already expensive to go into an Earth orbit, but there's no regular transportation to the moon. And without this, the lunar economy will not exist. And then once this problem is solved, we're already looking towards the in situ resource utilization. So today already we work together with mining experts from universities around the world and also mining companies to see how this resource utilization can be used and which resources can be gathered on the moon. Primarily, we're looking towards hydrogen and oxygen, which can be gathered from the water on the polar regions of the moon. But we're also looking at different metals that can be extracted on the lunar surface, which are vital to really build infrastructure on the lunar surface. And on one hand, it's where can we find those? On the other hand, it's how do we extract those? How do we transport them? And how do we process them on the moon? Because bringing anything from Earth is so expensive that we really have to limit this to make this sustainable. So in order to do this, we actually work together with a lot of partners. Already here in Luxembourg, we work together with the Luxembourg Space Agency to develop a polar ice mission. to find the water on the moon or have better information about where the water is and in which quantity. We work together with ESA, where we're trying to develop a commercial ISRU mission. We also work on the ESA's Prospect mission, where 2 of our scientists are on the scientific team. And we also work together with NASA. We're one of the 10 teams that have been selected to work on the commercial lunar payloads service. And besides that, we also work with a number of universities already here in Luxembourg, but also in the UK as the Imperial College, also in Japan. So Tohoku University provided us with a lot of know-how on developing mobility systems for our rovers. We work with the University of New South Wales and the University of Queensland to assess the mining technology for the moon. And we're also looking to work together with the University of Munich to develop payloads for the rovers. So yeah, as we mentioned, we were really looking even further than the actual landing on the mission. So the transportation is only one small step of getting a proper economy working on the moon. Planning is a big factor. So even before a mission leaves the Earth, we want to know what are the scientific goals, how we can achieve them, what are the technical issues of doing those, where do we land, how do we get to the place that we want to take samples. All of those are quite complicated, and those are services that we're really working on. We provide our own mobility for our rovers, so we're also interested in getting scientific payloads and putting them onto our rovers, because we know that not all scientific instruments come with their own mobility systems. We also develop mapping technology so that essentially any measurements that have been taken, they can be plotted on a 3D map, and we know exactly where they have taken in case someone wants to go back there. We also work on the evaluation of different materials to see how they can be useful for mining, how easy are they accessible, in which areas are they deep underground, how much does it cost to extract them, and so on. So this is more with regards to the work that I'm doing. So I work on the advanced autonomy. So one of the big issues we have on the moon is the communication delay. So the delay is about 1.25 seconds in one direction, which means 2.5 seconds speed of light in both directions. And then plus additional delays, you can end up with a 5-second delay from when you see an obstacle to when you can actually send the commands to get the rover to stop before that obstacle. So in order to really get that fast operation time, we're looking into using different sensors, including cameras, lidars, and time of flight sensor. We're looking to improving the localization on the rover so that the rover knows where it is and by how far it moved. We're looking into generating maps on board. This is really important for any autonomy so that we can know where obstacles are and how to drive around them. We're looking into more processing power because currently most space hardware has very limited processing power, and we really want to do as much processing on board as we can. For the scientific measurements, it's really important to know with absolute reference points where they've been taken so that they're actually valuable. And lastly, we're looking at autonomous path planning so that either we can suggest paths for the rover to drive so that our operators can take decisions much faster, or even to the point where we can get the rover to autonomously decide where it wants to go. So we only give high-level commands and then it can follow those. So that leads me then to the actual topic I want to cover today. So what's the difference between developing rover for Earth-based applications to rovers for lunar surface applications? So essentially, I'll be covering two areas. On the one hand, I'll cover the actual conditions of the moon and how you deal with them. On the other, I'll cover general problems of going into space versus doing things here on Earth. But let's start with the conditions on the moon. So Big issues that we have to deal with are the radiation environment, the vacuum of space because there's no atmosphere, the large distances, and the lunar day-night cycle. Let's start with the radiation. So any hardware that you send into space really has to deal with the radiation environment. Here on Earth, we're protected by the Van Allen belt, and there's very little radiation that actually arrives on Earth. But in space, this has a big implication for any electronics hardware because the particles that come from the sun and also the background radiation in space, they can actually flip bits on our computer. So that means that a value that was a 0 previously can now be a 1, and this can have big impacts on operating any hardware. But regardless of that, so this is even only one problem. The other problem is that the radiation can actually fry the electronics to the point where it's no longer usable, which is also another issue. So in order to get around this, there's special radiation hardened hardware that lets us, that can survive this. And on the other hand, we can also get around this with redundancy. By one hand, by having multiple processes running the same calculations multiple times and then voting on whether or not your result is correct. So that's one way, or you can have a single computer that does the same operation multiple times, stores them on different places in memory, and then compares them afterwards. But all of these things take a lot more time to implement, and that makes computers for space a lot harder than it would be here on Earth. Then the vacuum of space. So because the moon doesn't have any atmosphere, this actually makes it more difficult to build a hardware for a surface rover on the moon than, say, for the surface of Mars, because the implication is that the temperature fluctuations are much larger. So it's very difficult to dissipate any heat, and there's no body around the rover that can actually store any energy in that sense. So you really need to build your rover to deal with this temperature fluctuations. Because on the lunar surface, our temperatures fluctuate between minus 180 degrees during the nighttime and plus 100 degrees during the midday time on the moon. So this makes operation more complex. Also, if your rover is constantly looking towards the sun from one side, then that one side will heat up while the other side will cool down. So this might also put additional constraints on any operational concept. So yeah, as I said, this requires very good thermal management. Then the large distances. The moon is at plus minus 384,400 kilometers, depending a bit on where it is in its orbit. It takes several days to get there. This depends a bit on how your trajectory is. Usually, at least for us, we try to save fuel, so it will take a couple of weeks to get to the moon, just to be as efficient as possible. If you have more fuel or just a bigger rocket, you can get there faster, but it will also cost a lot more. There are communication delay and limitations to this delay. So essentially, because the speed of light is 1.25 seconds, you have to take into account that any command you send has a certain number of delay, and this also means any operation or remote operation has to be carefully planned, because you have to send the command, wait to see what the rover does, wait for its images to come back, and then take a new decision, and know that you can't react any faster than this. The other limitation is that because of the large distance, the signal has to be either very strong or you have to reduce the amount of data you can send. So we cannot put a big antenna on our rover because essentially it's limited in size already through the spacecraft we use to go there. But on the other hand, we try to use big antennas here on Earth to make up for this to a degree. but still there will be limitations on how much data we can send back. But all of these factors mean that we need to plan very well ahead. We plan already based on orbital data we have of the moon, and we have to plan very carefully how our rovers will be operated from Earth. Then the next problem is the lunar day-night cycle. So essentially, one lunar day lasts 24 Earth days because the moon rotates very slowly around its own axis, and actually it's locked so that the same side always faces Earth. The problem with this is that the lunar day lasts 14 days, and the night lasts also 14 days. That means you have 14 days of continuous sunlight, and the temperature can heat up quite a bit, as I said, up to 100 degrees. And then during nighttime, it drops because for 14 continuous days, you don't have any sunlight, and the temperature goes down to minus 180 degrees. Also, if there's no sunlight, you cannot generate any power. And if you don't have any power, you cannot use any heaters. And if you don't have any heaters, your spacecraft will slowly die from the cold. For our missions, this simply means that there's a reduced mission lifetime. We could build a rover that was pretty much only based out of batteries and radiators and insulation, but that wouldn't make a lot of sense because what we're trying to prove is we're trying to prove that we can land on the moon, and we would try to prove that we can explore the moon and gather scientific samples. So for our first two missions, we're not planning that our rovers actually survive the lunar night. If they do, that's great, but we're not putting a lot of extra payload weight into the night survival. Now, the other point I wanted to emphasize is the actual traveling to get to the moon. So here we deal with a number of factors like the launch vibrations, the payload mass, power generation, communication again, localization, the redundancy, and the testing for the moon. So already before we can get to the moon, we have to get into space. And while we build our own spacecraft with its own propulsion, we still have to use someone else's rocket to get into Earth orbit. And for this, we're relying on SpaceX. So we're happy to have SpaceX as a partner. But essentially, during each launch, no matter which rocket you use, there are a lot of vibrations that come from the rocket engine. And this means that everything has to build robust enough to actually survive these vibrations. So this adds a lot of weight to the actual spacecraft. But this also adds a lot of testing. So when we build any structures, we first do simulations on computers to check whether or not they could survive the vibrations. And then when we're happy with those numbers, we go to an actual testing facility with a vibration table where we shake our spacecraft with different vibrations, and then we see whether or not it can actually match this. This also depends on your launch vehicle. So if you use a different rocket, then you have to redo all of these calculations because they might have a different signature essentially, and you have to plan for this. Then the launch cost, you probably all know this, but it's expensive to go into space. So this is one of the graphs I found which mentions how much it costs to send 1 kilogram of mass into a low Earth orbit. So that's not even where we need to go. So we want to go to GTO, where then we can use our own propulsion. But even then, you need to bring your own propulsion to go to the moon. So if you want to send a kilo to the moon, you need to make sure that you also account for the engine you have to bring and for all the fuel that you have to bring to actually go from an Earth orbit into a lunar orbit, and then in the lunar orbit to land, to slow down, and then get to the lunar surface. So essentially, all of this means more costs on your mission. So you try to reduce the payload mass as much as you can. Power generation. So this is a big problem because there's no plug on the moon where you could just plug in. So all you have is solar panels. If you build a satellite, this problem is already an issue, but it's less of an issue because essentially you're in zero G and you can build bigger structures and they don't have a very big impact on how your structure behaves. But on the moon, we do have some gravity. And essentially, if we want to generate more power and we want to have bigger solar panels, that means we also need to build a bigger rover. And then we need to figure out how this deals again with the mobility. But at the end of the day, this means if we have a small rover, that also means we have limited power generation, as there's only so many solar panels we can tape on our rover. One possible solution that usually gets mentioned is nuclear power generation or radiothermal generators. They are also great, but they have other issues. They come with a lot of paperwork you have to deal with. So that's one issue. In some countries, you can't really work on them because the radioactive material is difficult to deal with. And also, they only produce limited amount of power. They are great for surviving the lunar night, but currently we're only looking at solar panels because the effort of using RTGs is an order of magnitude more complex than just solar panels. Then communication. So as mentioned also before, the large distances are an issue for dealing with communication on the moon. And we really have to decide which data we want to send back and which data we want to leave on our rover. This is on one hand for operation. So we need to figure out how much data we can send back to have a safe operation, but we want to keep that to a minimum. So for example, even if our rover has multiple cameras, we might want to consider only using one camera. We don't need color on that image, so it's already in grayscale to save as much data as possible. And even for scientific payloads, we try to figure out what data is actually necessary and which data we don't need, and at which time we can send it to Earth. Another issue is the visibility of the antenna. So essentially, if you want to operate your rover, you need to see the rover with an antenna here on Earth. There's not a lot of antennas we can use because we want to use the biggest antennas we can get a hold of, but there's not a lot of antennas that are bigger than 35 meters in diameter. So that requires different constraints on your mission concept. If you, for example, go to the equatorial regions on the moon, you will have good visibility most of the time. But if we now consider going into polar regions where we want to go for the water that is there, this is a bigger issue because there might be elements on the horizon like hills that can block the visibility to the antenna we want to use at that point of time. And this is a big constraint when trying to do path planning. So yeah, essentially there's a limited data throughput. You have to decide what you want to send back. And there's also a limited operation time. So you have to decide at what point can you access which antenna, and can that antenna actually see your spacecraft. Localization, so that's a topic that I work with a lot. So there's the issue we have is there's no GPS on the moon. So here on Earth, when you want to do autonomous driving for rovers, you can just put a GPS antenna on it, and this solves a lot of problems that deal with figuring out where your rover is and where you want to go. Currently, there's no existing GPS system on the moon. If any of you guys want to develop this, I would be very happy to see that. But in the meantime, we have to find other ways to do localization. And here we differentiate between two kinds of localization. We differentiate between absolute localization. So in absolute terms, where is my rover with specific coordinates in longitude and latitude on the moon. So this is important when you deal with orbital imagery. So for example, for some of the scientific concepts we're working on, we have data from satellites that have taken images, or also scientific measurements from the polar regions of the moon where we think there's water. But now when you're on the surface of the moon, you don't know exactly where you are in that satellite image. So it takes a while to figure this out. And that's where absolute localization comes in. And today, this is mostly done by hand. If we look at Mars missions, essentially, there's operators that look at the images that come straight from the rover, and then they look at the satellite images from the area, and they try to figure out where this actually is. After the mission is done, this is actually a bit easier to do because essentially you can wait for a satellite to fly over your lander, and you can actually take a photograph of it and then pinpoint the position. But currently on the moon, there's only 2 orbiters that can do this. So there's the Lunar Reconnaissance Orbiter and also Chandrayaan-2. But essentially, they will only be able to image your lander once a month if you're lucky. So if you happen to miss that window, then you have to wait, and your mission is probably over before you can do this. You have to figure out other ways to doing this. But as I said earlier, there's multiple ways of doing localization. So the other method that is being used for this is relative localization. So with relative, we mean that once you land and you boot up your rover, that is your starting position, and everything you do afterwards is with regards to that starting position. So when we plan any driving, we start our rover, we take some images, and then we say relative to our starting point, we want to move 1 meter forward and 0.5 meter to the right. And then we also determine that there's obstacles within this relative reference frame. So that's the other way to work with. And actually, even for robots here on Earth, relative localization is a big point, because the GPS accuracy is not always good enough to do certain types of operations. Sometimes you want to have GPS accuracy that's down to the millimeter for certain activities, and that's just not possible. So instead, you switch over to relative localization, and after a certain time of driving, you have an update of the absolute reference frame. Redundancy. So essentially, sending hardware to the moon is a one-way ticket. This is not only true for rovers, but also spacecraft. There's no one that can go and repair it. So if there's anything wrong, you're on your own. There have been examples in the past where this has not been true, like the Hubble Space Telescope, but there's only a handful of these examples ever. So essentially, you want to build your spacecraft so that nothing goes wrong. And in the case where something does go wrong, you want to have redundancy. So with redundancy, we mean that we want to have multiple components of the same type, or we want to have different components that could potentially take over the role that was needed. And for smaller companies like us, essentially the way we look at redundancy is also, we see, is this component critical to the mission? If this component fails, what is the downside? So we always have to see if, for example, the mission is completely over because a component fails. For example, if the communication system fails completely and we can't communicate with the rover anymore, then this is a real problem. So that's a component where we would have multiple redundancies. But for example, with autonomy systems, if the autonomy system fails, we can still remotely operate the rover, and our redundancy concept in that case is that while it's not great for the mission, it's not the end of the mission. And then with these types of analysis, you then take decisions whether or not you want to have redundancy in a certain component or not, and then you decide how you want to achieve this redundancy. Then we have testing and validation. So a big problem for all of these elements that I just mentioned is that it's very difficult to test them because we can't actually go to the moon and do our testing there. That kind of defeats the purpose. So instead, we have to figure out different ways of doing our testing and validation here on Earth. Actually, for my own work, one of the approaches that I use to do this is using simulated environments. So in virtual environments, we can test a lot of components. They're not perfect. You always have to be aware that, for example, when I simulate images from a camera, there's generally too precise and there's no noise the way there would be in a real environment. So the simulations will be one part of this, but on the other hand, we also want to get some real data. So while on the left here, you can see our virtual simulation environment. On the right, you can see the Lunar Yard we're currently working on together with the University of Luxembourg. And this is another place where we test our autonomy system. I gave you the example for the autonomy system on how we do that testing. If you use a look at other parameters, like, for example, the structure elements, you would want to have different kinds of ways to test these. So we have, for example, vibration testing to test the stability of the structure. You would use a thermal vacuum chamber to test the thermal parameters of your spacecraft. And in that way, every single subsystem will have different ways of testing their system. So the resulting rover requirements mean that we need to build robust rovers that can deal with the vibration. They have to be lightweight so that we can send them at a reasonable cost or even on any existing rocket. We have to deal with radiation protection and also with how the systems deal with any failure due to radiation. We have to build as power efficient as possible because the size of our solar panels is limited. We have to have a detailed mission plan ahead. So even before we land, we want to have a detailed mission plan where we detail if this happens, what do we do then? If we land here, how does that affect our future mission? We want to have redundancy in our system. So if one component fails, we want to have a backup for that component or a backup for the backup, depending on how important they are. And lastly, we want to have really good testing of all the systems. So we want to be confident that all the systems work. Again, here the same as with the redundancy. If a component is more important for the success of the mission, you probably want to do more testing for that single component than if it's only a bonus goal to achieve this. And this is the end of my talk. So now I'll be happy to hear your questions.
Thank you very much, Philippe. Thank you. It was a fantastic presentation. I really enjoyed learning about your background, about iSpace, but in particularly, I really liked the roadmap to lunar economy. And now we go to the Q&A session. So I see it's very active, the YouTube chat. Thank you, everyone, for submitting your questions. Let's start with the first one. What kind of simulations did you perform to the rover before going to the experimentation phase?
So here I can only really talk about the autonomy systems because that's my specialty. In terms of simulation, we try to test a number of different environments because one of the issues we have is we don't have a lot of data for what it looks on the surface of the moon. So we know where the Apollo missions landed and a couple of other unmanned missions, but essentially if we go to a new landing place, it could look a whole lot different and the satellite imagery isn't good enough. So what we do, we go into our simulation environment and there we test different types of rock, different number of rocks, rock distributions, different crater distributions, and then we see how well our systems can handle this for the autonomy systems. And we do the same thing when we go into our physical lunar yard facilities, where we also try different rock distributions, different type of surface materials, to actually be able to account for this. And lastly, also, if you do a field test campaign where you go to an area with volcanic rock, which would be similar to what you're looking for on the moon, then you also want to see, can we find different areas that would be able to map all of these different surfaces? Because essentially, when I ask our lunar geologists, what does it look like where we land, and I get one answer. If I ask another lunar geologist, they will give me a different answer, and so on. I'm not sure I answered the question here, so if you have a follow-up question, please.
Yes, no, that's really good. It's really a lot of information that we are not experts. So there, it's where you can enlighten us with this. So that's very good to know. Actually, touching about where to go to the moon, another question we have is, what are iSpace plans for the commercial lunar payload services program? Will this tie into a deeper collaboration with NASA, ESA, or iSpace for the Artemis program?
So essentially, we applied to the NASA CLIPS program to our partners in the US. So we work together with Draper to actually provide the lander. We applied to some of the existing task orders. Unfortunately, we were not selected for those. But in the future, we still want to apply to other task orders, and hopefully we can collaborate with NASA on that. It's always great to see space agencies to actually achieve this. We're also looking at doing this outside of the CLIPS program. So we're trying to work with ESA to do similar things, and we're already collaborating with ESA on this. And the same thing in Japan, we try to get JAXA to also try to actually fund missions like that, because one of the realities of private space travels to the moon is that in the long term, there will be, there's a need to go there. And if we can go there and build up a gas station to refuel rockets, that's great. But in the meantime, we still need to have some revenue to actually finance this. We have investors that have funded this so far, but any revenue we can have in the meantime to actually fund this makes it easier for us to actually build a business case out of this until we get this more sustainable business case.
I see. Thank you. Yes, well, good luck with your proposals in the near future, and maybe touch on the revenue side. So perhaps to have a business application here on Earth. Would you imagine that for iSpace?
So there are other companies that really look towards diversifying, in the sense that they've tried to find a synergy between an Earth-based business that they can apply to the moon as well. But in our case, we found that this distracts quite a bit from doing the actual going to the moon. So the way we look at this is we have managed to get the funding to actually go to the moon. So our primary focus is to actually apply that. If we can find a good use case on applying our technology here on Earth, then we will do this. But I mean, you've seen my presentation in the sense how different it is to build a rover for Earth than it is for the moon. So at this stage, we have not found the perfect case for that. And I think our focus is still more, we want to go straight to the moon, not to some other industry first.
I see. Yes, I understand. It makes sense. We have a question, actually, a special question from our Swiss astronaut, Claude Nicolier, who is watching live. He's asking, how do you plan to navigate precisely on the moon surface? Terrain mapping and storage of terrain data? Because it's valid in the vicinity of craters only, so it would not work for the Sea of Tranquility.
Yeah, that's actually true. If you work with digital terrain models, it really depends on how much structure you have in your environment. But that's why I said there's always different approaches. One approach is the absolute localization, and the other approach is really the relative localization. For the direct operation of the rover, the relative localization will actually do just fine. You can even have a lot of autonomy out of this. You won't know exactly where you are in terms of position, but you will always have a good idea of where your orientation is. So you can figure out your absolute orientation just by looking at the sun and the time of day. So you will actually know in which direction you need to head. And then in terms of absolute reference points, what we do is we look at orbital imagery and we try to figure out where we would be in that orbital image. So currently this is already being done for the NASA missions on their Mars rovers like Curiosity. When they land, they don't know exactly where they are. There's a specific landing ellipse, and within that landing ellipse, they try to figure out where they could be. And currently it takes about a day or a day and a half to actually determine those positions. And they have to do this through a very manual process where they try to make a virtual satellite image, and they compare the actual satellite imagery with their virtual satellite imagery. One of the ways we tried to improve this process was to use machine learning. And we actually proved that you can improve this in the simulated environment. And we hope we can actually also improve this on real data in the future. But so far, we're still working on that.
No, that's good to optimize. It's a really time-consuming task, so it's worth a shot to optimize it and shorten the time there. A follow-up question on this topic is, would it be conceivable to have antenna relay receivers on the moon's hills?
To have antenna relay?
Antenna relay receivers on the moon's hill. So on the top of the crater, I would say it's referring to.
Oh, so in terms of communication, yeah. So
Exactly.
one of the issues that we also have is that our current rovers, they actually use the lander as a relay station, and this limits the distance you can drive. So yeah, of course, if you can put a relay somewhere, this drastically extends your mission range. There have been other rovers, like for example, the Chinese rovers. They actually use their own antennas to, their own antennas directly on the rover to have direct communication to Earth, and then they don't need these relays. But in this case, I think the question was maybe related towards localization. So you could potentially also have relay stations that do the triangulation, same triangulation you would do with GPS satellites to figure out the position. But all of this means you need to bring more mass. So in general, we try to really look at, while this will work, can we do it without the added mass of doing this? Because at the end of the day, it always comes down to how much does this cost.
I see. I have a similar question. I think we would get a similar answer. It says, would fixed beacons attached to landers spread across the lunar surface allow for triangulation to help with robot localization?
Yes, it definitely would. But here, one of the issues will be that, first of all, you need to place them. So you need either you need to drop them while you land, then you need to figure out where their position is. And if they happen to land in a valley rather than on top of a hill, their range will be quite limited. But this is an approach you could use. You could even use an approach where you have multiple rovers that are driving, and they actually localize each other, and you only have one rover that moves at a time. So you have two rovers that are standing still. They look at the other rover and see him drive, and then one of them stops, and the only one moves. So there are a lot of concepts. But again, now we increase the problem by throwing more rovers at it, or by throwing more beacons at it. It's a bit similar than the GPS. If I had 24 satellites to bring with me that could actually provide this signal, and that would be great. And I think at some point in the future we will also have this. But until we have this, we really try to be smart with the technology we have, and also be smart with what our mission limitations are. Does our mission actually need this? or can we do other ways of doing this in the meantime?
Okay, so the bottom line would be to bring the less as possible to the moon because of costs, mainly. Yes. Okay, I see
Yeah.
that. Thank you. Another question we have, is it possible to receive data from LiDAR sensor mounted on a rover operating on the moon for 3D mapping an area? If so, what are the mechanisms to compress the data and send them to Earth?
So it's definitely possible. The issue is more LiDAR sensors are relatively big in compared to a camera, so they bring a lot of mass, they produce quite a bit of heat, and they need a lot of power. In terms of data generation, they actually don't produce a lot more data than what you would have generated through imagery. Actually, you would produce less data than what your camera images produce. The compression, you cannot compress it quite as much, but essentially LiDAR so far have not really been used in space just because the technical implications of making them ready for space have been too difficult, and LiDAR sensors also haven't been around there. There are actually only 2 or 3 LiDAR devices that were actually built for space, and some of them are huge. They weigh 20 kilos, and essentially they will be bigger than our rover to bring. But in the future, I would actually see this as a solution because we actually, for our Google Lunar X quest rover, we used an approach that's called a time of flight sensor. It's similar in the data that it produces, but we managed to actually space qualify this. So in the future, I see this as possible, and I don't actually see the data as the bottleneck here. The mechanical, surviving the launch vibrations and the mass are more of an issue.
That's good to know, because actually we have a team in the IGLUNA, student teams from Romania. They are working on this, on the rover with a LiDAR system to do the 3D mapping. So it's good to know there's good possibilities for them to continue developing in the future and maybe seeing it in the moon one day, their concept. That's great. On a different topic now, we have about radiation. How much is the radiation dose on the rover per day?
I have to admit that I'm not exactly the right person to answer this, but the issue isn't more the dose of the radiation, because when you deal with this radiation, you look at 2 factors. You look at the total ionizing dose, so how much radiation is actually coming in general on your hardware. And most hardware, even commercially off-the-shelf hardware, can actually survive this for the mission lifetime we have. So on that side, because the mission lifetime is so short, it's less of an issue for us. But the bigger issue is the single event upset, where a high energy particle hits a part of your electronic component and has a high voltage current that provokes a latch up on the device, which is either temporary, where you can power cycle your device and hope it reboots, or it can permanently latch up a transistor, and then that transistor won't work anymore properly. So this is really what we're more afraid of than the total dose of radiation. And to get around this, redundancy is definitely one way, but you can also try to look at it through software redundancy, where if a part of your system is broken, can you still use your chip? Can you get around it? Or for those temporary latch ups, can you still operate? For example, when you have such a latch up during the landing of your spacecraft, you cannot really power cycle it, because essentially during the landing phase, you don't want to reboot your computer. But if our rover's on the ground and it has to reboot, then it reboots. It's not a big issue. It's not going to fall anywhere. But the lander, if that happens, then it's essentially will crash into the moon. There's no time to reboot.
That we don't want that to happen, so it's smart to think about that.
Yeah, so in that case, you want to have redundancy. Really, you want to have 2 computers that do the same processing at the same time.
Good. Now, going to another topic, the students also have the question, what advice would you give them actually if they would like to work at iSpace?
Oh, have a look at our website. We regularly post job offerings. We also have interns that come and work for us. So we also try to put those intern offerings on there. So definitely have a look. Be enthusiastic. We have quite a number of people that actually come from non-space backgrounds or that shifted over into space backgrounds. I think the major difference of working for us rather than working for something like a space agency or a big company like Airbus is that we need people that uh, can work with a lot of different factors. So we don't need an expert in one very narrow field. We need an expert in his field, but he has to be able to do a lot of different things at the same time.
That's good. We hope one day to see the IGLUNA students maybe being employed at iSpace there to expand our network. Good. Before we close, maybe one last question actually to get to know you better. They were also asking if you had the opportunity to leave the Earth, to live on the moon, would you do it?
On the moon, yes.
Great.
I've been asked this for Mars, and currently I would say the Mars is too far, but the moon is still within a reasonable distance where I can follow my Twitter feed. So
And come
yes,
back.
and come back, yeah.
Exactly, that's important too. Great, thank you very much, Philip. With this, I would conclude the session as we are closing now to the hour. I would like to invite everyone to please stay tuned for the next session tomorrow. So we are done for today. And tomorrow we start with P3 SWAC team at 11 hours Central European time. And for our viewers as well, besides thanking you for joining us, we would also like to ask you to please fill in the survey here in the video's description for us to get to know you better. So everyone, thank you very much for watching, and especially thank you, Philip. It was great having you as a guest. Thank you for your time and your talk. We actually learned a lot about all the mission concepts in the designs and operation of rovers in the moon. It's really challenging, and it's really great to hear your insights. Have a nice afternoon, everyone, and see you tomorrow.